Good morning, everyone. Welcome to the TRIAD lecture. And today, Professor Johannes Schmidt-Hieber will continue his lectures on deep learning. And today, his lecture is about a statistical theory of deep ReLU neural network. So let's welcome Professor Schmidt-Hieber.
So thank you very much for the introduction. So one announcement that the next week on the last lecture is on Monday. It's not on Wednesday, right? So just that you know and that you're not confused. Okay. So what have we been talking about last time was mainly about advantages in terms of approximation properties through additional hidden layers. And we stopped essentially around this topic with what now are specific properties of deep value networks. And today we will continue with this, and then we will go further, and we will develop more approximation theory for the deep value networks, and then apply that to statistical problem. And depending on how much time is left, I will then in the end talk about how you can relate these statistical bounds to the bounds that you would obtain for other statistical or machine learning type methods. Okay, so before I start, I just want I copied the slide from lecture 1 here again, because we will use this notation a lot again. And this is just how we define a neural network, right? So we said we define these neural networks as where we always alternate between matrix vector multiplication and then component-wise application of the activation function. And we introduce these biases or shifts in every layer, and they're called V1 to VL, and the weight matrices are called W0 to WL. The depth of the network, the number of hidden layers, is always denoted by L, and P. This vector P says how wide the network is in each of the layers, starting with the input layer, and then the last entry is the width of the output layer. And so the width of the network essentially says how much you can store in your network, right? It's a sort of storage or capacity type thing, and the depth of the network says something about how much computations can you do within your network. And so you will always see constraints on the network architecture expressed in terms of the depth L and the network width P. And we will always talk today about the ReLU activation function. So this is just an old slide. And so the last bit I was talking about was that what you can do is you can, with additional layers in the ReLU network, you can build functions that contain of many linear pieces, and they are just parameterized with few network parameters. Okay, so we had this upper bound saying that if you have such a ReLU network with vector 1, P1, PL to 1, so that's just a function, a univariate function, but then the width in the hidden layers can be large. And then there's this upper bound on how many piecewise, how many linear pieces you can have, and the upper bound is given by that. And you see that the number of parameters is something like the sum over pi times pi plus 1, the number of entries in these weight matrices. But the number in the upper bound is something where the product occurs, so that can grow much faster, of course, than the number of network parameters. So which means you can generate highly complex objects with rather few parameters. And now you can say, well, maybe this is a bad upper bound, and so you have to also show that there's a lower bound. And that's a construction that we will use later again, and therefore it's nice to introduce that here. And the construction is as follows. So you take a function t, so that should be here 0, 1 interval, and typo. And so you take the function t just does that. Okay? And if you apply t to itself, then you get this. And every step that you do is you double the number of these triangles. Yeah, so if you have t to the t composed with t, you get 4 and then 8 and so on. And so this is what this function rk is. The function rk consists of so it has, if I'm not mistaken, it has 2 to the k of these triangle functions. Yeah? So that is a function that consists of, if you see it as a function on R, then it's a function which has 2 to the k plus 1 plus 2 pieces, linear pieces. Okay, so it's and here's the way you can build this function by a network, by a deep value network, and I hope you can see it. It's a complex thing. So so what you do in the first layer is you just so you use this representation. So t of x can be written as a difference of two value units. And so that's what you do is you just build this function and then you just iterate the thing by stacking layers on top of each other. So in the first one you get the input x, and that computes the 2x and then applies the value. And here you get the maximum of 0 and 4x minus 2. And then if you combine that, you get the t of x. And here in this layer, you don't apply the activation function. And then you just iterate that k times. And then you get the tk. And here's so because here we don't apply the activation function, that means somehow we just have here 2 linear transforms which we can collapse into one linear transform, and then if we really want to write it as a linear as a deep value network, then we get that network, and it has, you can check, it has k hidden layers, and each hidden layer has 2 units. So in total it has of the order of k units, and it generates something which has an exponential number of linear pieces. So 2 to the k with the number of network parameters of the order of k. Okay, and we will come back to this construction later. It will be actually useful for the approximation theory. Okay, so one important thing is that you want to do with a network, you want to approximate the multiplication operator. Okay, so this is something which is not really intrinsic within this network structure, that you can multiply or build a network that, given 2 inputs, gives you as an output the product, or a good approximation of the product of the 2 inputs. Yeah, because of this structure of the network, they are not really built to multiply inputs. And so actually what you can do is, for the approximation theory, whatever you want to do, somehow you have to think about this problem at some point. And what you can do is, you can essentially, with the multi-layer network, you can reduce that to the question how you can approximate with a network the square function, right? Because by polarization, you can write the product, you can write it as in this form. So you can essentially, in the first layer, you get your, right? So you have a network x and y, and you want here that the outcome is something like xy. And then so what you can do essentially in the first layer, you can compute x plus y over 2 and x minus y over 2, and then you apply, okay, so suppose we don't put here the activation function, so then you apply your network which does the squaring, okay, whatever that is, that's the thing you have to figure out. So that will give you x plus y over 2 squared. Here you also apply the squaring network. That will give you x minus y over 2 squared. And then you just subtract them when you get something x, the x times y. Okay, so the whole thing, if you want to approximate multiplication, then what you have to think about is how to do this, the square function. Okay, so actually this is something we already discussed in this one proof I showed you in lecture 2 when we were talking about the shallow networks. This is something you can also do with the shallow network if you assume that your activation function is, say, twice differentiable, and the activation function itself is not a linear function. Then there must be one point t where the second derivative is non-zero, and you can just use finite second order difference to approximate the second derivative, and then if you rescale everything, you get here the x squared for h, if you make the h tend to 0 in order to achieve this convergence. And that's something you can, the left-hand side here, this is something you can build with a shallow network. But what you have to do is, of course, you have to let the h tend to 0 in order to get a good approximation rate here. And that means, so the 1 over h that you have here is, or the 1 over h squared that you have here, that will become, of course, very, very large. Okay, so that forces somehow the network parameters to be large, which we somehow want to avoid, because we want to show that if we initialize with small values close to this close to the initialization, there should be a good solution. So, and if you make the network parameters large, that means somehow your training algorithm has to go very, very far potentially in order to find a good solution. And what we will see now is that for these deep value networks, you can use a completely different construction that is not based on this argument. Here you should also see that you couldn't do that for the value, because it's it's not twice differentiable, and it's not even differentiable at 0, and therefore you can't do that. Okay, and now we come essentially back to the same construction that I have shown you before. But it's a slightly modified. Okay, so why is it modified? Because somehow I really want in these proofs in the approximation theory, I want to show that I can do the approximation theory with network parameters that are very small. Okay, so I try to make them as small as possible. Maybe not smaller than 1, because 1 is always, then you can learn still the skip connections, which is somehow what we discussed last year and last lecture, and have somehow the identity mapping in your network, but you don't want to have them large. Okay, so you want to show somehow close to your initialized network there's a good network that has good approximation properties. Okay, so because we want to do that, we have to modify everything a little bit. So we introduce now, okay, they are also called TKs. And the TKs are essentially just the same as before, but now we rescale them such that they somehow here 2 to the minus 2k, and here we have 2 to the 2 minus 2k, something like this. But this is still otherwise it's still the same thing, and it allows us to make the network parameters smaller. And then we define Rk as the composition of these T1 to Tk. Okay, it's essentially the same thing as this Rk before, but now it will have, so the height will be different of these triangle waves that we have in here. But they still will be of an exponential. there will still be something like 2 to the k of these triangles in Rk. And as I have shown you before, this Rk is something that we can build with a deep value network. And actually, you can convince yourself that this Rk, you can build it actually with a network where all the network parameters are bounded by 1. Okay, so for instance, if you look into here, so how large are the network here? Here you need network parameter 1/2. Here you need network parameter 1. Here you need something like 2 to the 1 minus 2k, which is always smaller than 1/2, and so on. So you can check that by hand more or less that all these network parameters actually can be taken to be less or equal than 1. And then the result is the following. The result is that it's not exactly the square function. It's the function that looks like this. So it's x times 1 minus x. And that one you can, if you sum all these triangle functions, if you sum them up, then you approximate this function up to order 2 to the minus m. Okay, so how does that work? So the first R1 function just approximates this function. Okay, so that takes out this part. So that means we are left with, after R1, we are left with approximation of this remaining bit. And this one we can do with R2, which is this function, and it subtracts essentially just, it interpolates at dyadic grid points, and then afterwards we just left with those bits. Okay, so it's a very geometric object. If you just draw everything, you can easily see and convince yourself that then such a bound is true. And it's not very different from x squared, because we can just subtract. We can just subtract the linear function here, and then we have and multiply with -1, and then we have the square function. Okay, so what we have seen before is we have seen how to build the function Rk, and now we have when we have seen that you can do that with a network with two units in each of these layers. But now we have a sum over these Rk's, and then you see this property from before. Okay, so what I mentioned, why the value is so attractive, because what you do is essentially, so you have different networks. So something like, so say this network that builds you the function R1, and this network builds you the function R2. And they have different depth, right? So we know for Rk you need k hidden layers. And now we want to somehow compute the sum with such a network. And what we can do is essentially we can now, so Rk is also the same as Tk applied to Rk minus 1. So we can somehow build Rk, and then from Rk we can go to Rk plus 1, and then at the same time we also store the value of Rk. Okay, and we can store that with one additional hidden unit. Okay, so the width of the network, if you make it wider, you can store more objects. So that means instead of 2 units in each layer, we need a third unit that stores the values that have been computed up to that point, and that essentially is passed through the layers by the identity. Okay, that's essentially the construction, and then you need width of the network of order, like the width will be 3, and the number of layers that you need to build and this network is m. Yeah, so you need m hidden layers because you need to compute R to the m, which is the most complex object. For that you need m hidden layers, and the approximation quality that you get is 2 to the minus m. So you get, you have essentially of the order of m network parameters and you get approximation quality 2 to the minus m. So you see with few parameters you can get very, very good approximations. Okay, so that's just what I mentioned. With these deep value networks you can do exactly this. And you can compare it with shallow value networks. Okay, so how good are shallow value networks? And for that you can also give really a lower bound what they can achieve. Because if you want to approximate this function here with a shallow network in one dimension, so a value network is a piecewise linear function, right? And the number of pieces is in one layer is just tied to the number of units in the hidden layer. Okay, so if you have every unit in the hidden layer gives you one additional piece. And so all what you have to do is somehow you have to find a lower bound of how many pieces do you need, how many linear pieces do you need in order to get a piecewise linear approximation with approximation to quality 2 to the minus m. And that's a thing you can solve independently of networks, right? You can show that somehow the best thing to do is just have an equal equidistant grid here, and then on each of them you can make such an approximation. That's the optimal thing you can do. And then the linear approximation, so you need 2 to the m over too many linear pieces. Okay, and because you need that many linear pieces, that means if you have a shallow network, you need that many units in your hidden layer, square root of 2 to the m. And now if we compare the deep value networks to the shallow networks, we see that we can approximate that if we fix the approximation quality with much less parameters. And this is really it's a lower bound, but it's also an upper bound. You can also show that this is an upper bound. So this is really what you need for a shallow network. And here you see a clear gain of the network depth. Okay, so how do we do now the multiplication? I essentially mentioned that already in here. And the lemma is now you can, I'm not going to prove it, but I just somehow the heuristic is quite clear. So you need a network which has essentially length or depth m, and it has width 6 in every hidden layer, and so we get 2 inputs and one output, and it computes the multiplication up to an error 2 to the minus m on the unit cube. And it exactly follows this program. So you first split it in this and that part, and then you do the square root functions. There's one little thing here why it's not exactly that easy, namely the x minus y over 2, that can also be negative number, and if you apply the value activation functions to that, then you set that to 0, so it's gone afterwards. So you have to make sure that this is always a non-negative, so you have to add here something and you have to calibrate it a little bit. Okay, so then we have seen that for each of these squaring networks that do the squaring, we need the width 3. Okay, so we have 2 of them in parallel. So in total, the network width is 6, and that explains these 6s that occur over here. And there's something which I find very strange about these networks. I think that in a sense they're a bit inefficient here. Inefficient, because essentially what we want to do is we want to square 2 numbers, 2 different numbers, and so ideal would be that you build the square function once with one network, and then you pass the through numbers through this network that you have built. But if you see, so what you want to do is, in a more abstract way, you have one function f, and you want to evaluate it at x, and you want to evaluate it at y, say. If you do, I don't know, if you construct something, you would say, well, okay, I construct somehow an abstract function f, and then I evaluate it at x, and then I evaluate it at y. With these networks, it's not possible. For every evaluation, you have to build this function f separately with the feed-forward network. So, and therefore we have to build this function x, the subnetwork that does the x square. We have to build it twice in the network, which is, I believe, is somehow there's some inefficiency in here that cannot be avoided with the feed-forward network. Okay, so in here it's just, okay, maybe I jump over that. It's just the way how you do this network construction then in order to approximate the multiplication. So that's the first bit that you need to do. And the second thing is that you can do with the deep network, we have been talking about this last lecture, is you can localize with it if you have at least two hidden layers, right? And so how do we localize now here? And that will be very helpful for the approximation theory. And so the way I showed you the localization with two hidden layers for the value activation function, that was again a construction that required the network parameters to go to infinity. So that was, right, so something like you want to approximate the indicator function on 0, 1, say, and the way you build your network is you make it look like that by make the increase and decrease very steep, and that requires that the parameters have to go to infinity. The construction here is different, and it shows that you also can do localization with bounded parameters. And so what you do is you say you're in one dimension, and then you build a discrete grid. Okay, so you pick a number m, and then those are the points j over m. And around each of these points, you build a triangle wave. And so on. And if you now add up all these waves, what you get is this function, right? So here's 0 and here's the 1. So it's the identity. So that means if we now look into so what we get here is we get right, the sum over these triangle waves is the function 1 on. We're just interested on 0, 1. So don't look at what happens outside. So if we sum them together, we get 1, and then we just multiply 1, so that gives us 1. And then if we rewrite this, the sum and the product, if we just invert the order, we get that we can also write it as if we take in every direction we take these triangle waves, and then we multiply them together, and then we sum them over all grid points. If we extend the grid points to 0, 1 to the d. Okay, so that means now what we have a sort of partition of the unity, and what we can do is we can take those functions and as localized functions. And they, if we add them all together, we get the 1 back, which is a very useful property. And those ones, you can see that we can build them now with deep value networks, because the inner part is very easy. So okay, absolute value is you have to be a bit careful, but somehow you can do that with, I think, 2 hidden layers. You can build this function exactly. Okay, so there's no approximation to do that. And then we have to approximate the multiplication operator, because we have to approximate our multiplications, and then we get these localized functions. Okay, so and what we want to do is we want to build this local, somehow an expansion with respect to those localized functions. So in classical statistics, also we often use an orthonormal basis, and then we by tensor product we make that, and we start with an orthonormal basis in 0, 1, and then we make it an orthonormal basis in on 0, 1 to the d by tensorization, and that gives us the basis that we use to expand the function in. And here we construct a different type of function system that is local, and they overlap, and you can also see, so they have very good properties because of this partition of unity property here. And we can build them easily with the deep value networks. Okay, so the second thing is, once we have built those functions, we have to assign a coefficient to them, right? And then we expand it later in a series, and that gives us the function approximation. And so how do we, what coefficient should we put here in order to give the weight of the function at that point? Well, this is, so what you want to do is you want to do also a local Taylor approximation around any of these grid points that you can then take somehow and multiply with the localized functions. And local Taylor approximation is also possible because it's just based on you have just to be able to compute monomials of any given order, which you can do if you can do multiplication with a network. Okay, so that's the multivariate version of the Taylor polynomial up to order beta, which is then later the smoothness of the signal. So if your function has beta derivatives, that means something like all these derivatives exist, and you can write down this polynomial, and it's written in this multi-index notation. So that means alphas are vectors, and this here means the product here. That means also the product of all these factorials, and it means you apply the derivatives with respect to all the directions after each other. Okay, so that's standard basic calculus, and you can rewrite that. You can rewrite that in terms of monomials, where you then get coefficients C gamma, which somehow depend on, you can write out what C gamma is in terms of these derivatives and the point A. And that's something, okay, so that's because we know how to do approximate multiplication. That's something we can, the right-hand side, we can also build with a network. So, but that only approximates the function f around the point A. And now together with the localization, we built this localized function system on each of these. Whenever we have localized, somehow we take on this local neighborhood, we take this function, this approximate function via the Taylor approximation in order to approximate the function f. And all of that can be somehow done within a deep network. And there are, of course, many technicalities that one has to take care of. And if you want to see all these things, you can look up my article on that. Okay, so that gives a major result that tells you about how well you can approximate a function of a given smoothness with a deep network. And so we say that the function here is beta smooth, and I always understand it as beta Hilder smooth. If you haven't heard about Hilder functions, just think about beta times differentiable functions here. And so they map from 0 to 1 to the R to R. So R is the input dimension. And now what you can do is you can choose parameters. Okay, that later tell you something about the approximation rate that you get, m and n. And this parameter m is essentially the depth of the network that you have to pick. And the parameter n is the width of the network, an upper bound for the width of the network in each of the layers. Okay, so if you take a network of this size, and if you also, suppose you take a network of depth m and width capital N, and then you can find within this class you can find a network, a specific network that has at most n times n non-zero network parameters, such that you can approximate this function f. You can approximate it with a network, so the network here is denoted by f tilde, up to a subnorm bound that is given by two terms. So the first term is the n times 2 to the minus m. I will come to that in a second. And the second term here in the upper bound is the classical approximation rate, right? What we have seen before for other approximation parts. If you have capital N parameters, you should get the rate n to the minus beta over r for beta smoothen functions in r dimensions. Now, this is not entirely right here because the number of parameters that you use, the effective number of parameters, is essentially of the order n times m. So that should give you also something better if m goes to infinity, and that is somehow missing here. So it's slightly suboptimal. And so what that tells you is somehow you shouldn't make the m too large. Okay, so this approximation bit here tells you if you make m very large, the bound is not that good because you use too many parameters to get a certain approximation rate. But the first part just tells you should make m also not too small because otherwise you're completely screwed up. This one is n, so that will be large. So you have to make the m large enough in order to kill this term. Okay, so m to be something of the order log n, log capital N, right? That should be right in order to make that of a smaller order than the second part. So you see, you get here essentially, if you do that, you get here something like capital N times log capital N, and so you get a log factor here missing in the approximation rate. Okay, and now so that's just playing around with the m and the n, but if you look what m and n are, this is the depth and the width of the network. Okay, so that it tells you something about. Okay, so the depth of the network should scale something like log of this capital N, and you will see that coming back later in the main theorem about the statistical estimation rate. The second thing you can wonder is you can say, why did I put this additional constraint in here that the number of non-zero network parameters is bounded by n times m? Isn't it the case that a fully connected network has number of parameters bounded by n times m? No, right? Because those are you always have to keep in mind those are square matrices. So the network width is n, but that means somehow if a matrix has then n squared entries, so the number of network parameters in a fully connected network would be something of the order n squared times m. So in here we require n times m. So that means somehow the signal, not everything is connected to anything. So it's not right. Otherwise, it's like very autistic brain where everything somehow connects to anything. So what it means somehow you see that in these constructions as well. So the signal processes quite linearly through these layers. So there's not too many interactions. So you get the number of outputs in one unit that doesn't go to all the other units in the next layer. So there's a lot of parallel structures in this network. And if you do the approximation theory, it's quite natural to have such a constraint. Okay, so that's what I already said. Now we from this, based on the approximation theory, that doesn't tell us anything about how the network can perform if we really have a data set and if we have data, right? So that's what we want to study now. In order to do that, we need, of course, somehow to say what the data generating mechanism is, how the data were generated. And what we do here is we study one famous statistical problem, namely the non-parametric regression model, which has been widely studied in the literature. And you could argue, of course, that this is a bit too simple because in the real application where the deep learning has its full power, those are very highly complex problems. But my argument is essentially that, well, maybe it works for complex data structures very well, but it should also work for simpler models, because if it doesn't work for simpler models, then there's something wrong, and this is a sort of a sanity check where that also does the classical statistical problems where it also can do that in a good way. So, okay, so this is, if you look into the literature, this is how people frame this problem. Okay, so they would say, well, I'm not talking about, so this is the way, yeah, it's the classification is typically explained, and so you have you get to see a number of labeled images, and say it's either cat or dog, and then as a very basic a model, you can say, well, okay, suppose I have a function that is unknown to me, and given these pixels, it always it takes all the pixel values of these images and then returns either cat or dog. And so what I want to do is somehow from the data I want to recover this function f. And then so what I can do is I can fit a network to the data, and that will give me the network as seen as a function will give me a function that should closely resemble this unknown function f. And I can try to bound the difference of the estimated network from the true network f here. Okay, so and if I have more data, I know more about this unknown function f, so I should come closer to the function f. Right. So the statistical problem is then to determine the rate of approximation at which an estimated network converges to the true underlying function. As the sample size increases, and then we are interested mainly in the exponent at which the rate decreases. And so this is now the rate we have been somehow that we studied. So for the non-parametric regression model, you get n observations. They are IID, and you get n inputs, x1 to xn, so this is what you stick into as input into your model, and then you get real valued responses, y1 to yn, and so the statistical model tells you how the inputs and the outputs are connected. Okay, so you suppose the data generating mechanisms like that, you get your input, and then you have an unknown function f, and the label that you observe, which is here. So it's regression, so it's a real valued thing. That is this function applied to xi plus some random noise on top of it. So what you want to do is, like on the previous slide, you want to use your network fit in order to reconstruct this unknown function from f from the data. Now, so what makes this model particularly attractive is that we know a lot about information synthetic properties of this network, what are the best optimal rates, and so on and so on. And it has been studied by many other methods which are widely applied in statistics, machine learning, and so on. For instance, the smoothing technique, wavelets, splines, and so it's really well understood. So that's a good case to study the deep networks. And it's also not too difficult. So here we take real valued responses. Somehow, if you would take, you also can phrase it essentially as binary classification problem by just looking at this rather as at the conditional expectation. And then it also covers the binary classification as well. Okay, so now what is the estimator that we take, right? So we have to specify given the data, we have to say, how do we reconstruct now the network? And in practice, of course, you know how it's done. It's all these variations of the stochastic gradient descent. And that's, of course, not feasible in a sense. And the way we model this is as follows. So we fix a network architecture. That's what people in practice have to do as well. So we say we fix a number of layers, and we fix the network width in each of these layers, which gives the vector p. And we also now, on top of that, you have seen it already, we fixed a sparsity s, which means number of non-zero or active parameters in the network. We don't say where they are. We just give a bound for that. And then we just write out or define the function class of all network functions that with this architecture, and this sparsity bounded by little s. And then the results that we have, they don't say exactly you have to take this estimator or that estimator. It just applies to, you will see that in a moment, it applies to any estimator that takes values in this class. Okay, so that means somehow you get, that's a function, a measurable function that gets to see the data, or it maps from the data space and it returns to you. It returns a network which it fits the data well. And then because we have to, before we can say something about convergence rate, we also have to say with respect to which loss we are considering the rate. And there's one natural loss function here. And this is the prediction error. So that means somehow if you get to see a new x, which is independent of your sample, you want that your estimated network predicts the labels as good as possible. And then you're somehow, it's natural to consider this risk function. And so all what we want to do is we want to find a bound of this risk function dependence on the sample size n. Now I have, I think, 10 minutes left or so, and I just want to go to the main result. So what you could do in principle, so how would people frame that? They would say, well, okay, so suppose that the true regression function that we have in our model has a certain smoothness, say beta. Okay, it's beta times differentiable. Now let's look how good the network performs on this problem. And if you do that, you see that from an information theoretic point of view, so the best method in this model can only achieve the rate n to the minus 2 beta over 2 beta plus d, whatever you use. Yeah? So there's nothing you can do better than that. There's not much more information than to achieve this accuracy. And the problem is that this rate of convergence, it suffers from the curse of dimensionality. So if the d is large, the rate is very small, and in practice the d is large. So that means whatever method you use, if that is the problem, any method will fail in order to reconstruct the function f. So what we rather should try to do is here we should try to find a good constraint on the function class that allows us to get fast rates, and where we believe that these applications where the deep networks are successful, that they satisfy this constraint. Okay, so that's what we want to do. So we want to find a good structural assumption on this underlying input-output relationship that we don't know and that we want to reconstruct with the network that somehow allows us to get fast rates, and that is natural for the applications and the neural networks. So here's, okay, so it's just a sort of heuristic. What you can see is that sometimes, or many of these applications where the deep networks are successful, they in itself have a sort of hierarchical structure. Okay, so if we look into the way the human vision works in our brain, so you get I get to see an image, a table or so, and that goes into the image goes into my brain, and it goes into brain regions V1, and this somehow takes a more abstract representation of that, and then sends it to another part in the brain, say V2, and that somehow in each of these brain regions, somehow the representation becomes more and more abstract until you realize, okay, so this is a table or this is a chair. And also other things like, if you want a way you could generate text is you could first generate lines. From lines you can generate letters, from letter words, from word sentences, from their paragraphs, and so on. So you see there's some sort of hierarchical structure, and each level we have objects that we then use for the next level to build a more abstract representation. And the thing is, with all of these applications, and this is the thing where the low dimensionality comes in, is that we typically, if you think about this heuristic, in each of these abstraction levels, we just combine a few objects into the next. So we can build a lot of objects, but only a few are used in order to build the next abstract object. So for instance, you just use a few letters in order to build a word, and not all of the letters that you have, and not all of the words are used in order to build one sentence. You just make a small, you just always take a small subset. Okay, so that's the thing. And now how do we write that into mathematical language? Well, the thing is that we say we suppose that the true function which we want to recover, that also has a representation as the composition of q plus 1 functions g0 to gq. Okay, so and from the previous heuristic, you could think, well, so these GIs, they can map from very different spaces to other completely different spaces. But here what I do is, for simplicity, I just assume the GIs are maps from R to the DI, say, to R to the DI plus 1, and the DIs, they can be anything. And so the GIs, they are now assumed to be beta I smooth. And the thing I mentioned on the previous slide, they typically we allow that the GI components, they don't depend on all of the available variables which are DI, right? There are DI many variables here. And we just say, well, there's another variable TI, and TI is smaller or equal than DI, and the GIs only depend on TI many variables. And you should think about the TI as being much smaller than the DI, maybe 1 or 4, and the DI maybe 1,000 or so. Another thing that we have to fix before I can state the result is somehow the quality of the way we can recover the function f here in the regression model is because we can separate it from the noise because of its different smoothness properties. So if we now impose smoothness on these GI functions, we first have to study what does that imply in terms of the smoothness on the f. Okay, so we have somehow to look into so what is smoothness on the f's if we have smoothness beta I on GI. And if you, for instance, think about a Brownian motion has essentially smoothness 1/2, and if you do iterated Brownian motion, so you apply Brownian motion to itself, you see this iterated Brownian motion is known to have smoothness essentially 1/4. Okay, so you lose smoothness by composing function, and that happens here as well. So these effective smoothness indices, so essentially the smoothness that is implied on the f, are then given by beta I star, and this is given by this formula. And now everything in terms of the rate, all what you have essentially to remember is that the function f can be represented as in composition of this form, and what the TIs and the beta I stars are. The other things will not matter. Again, so this is the Q here has nothing to do with the depth of the network. This is an assumption that we make on the underlying thing that we want to learn with the network, but it has nothing to do with networks. It's just the way we model the data generating mechanism of the inputs and the outputs. Also want to mention there are many related results, but yeah, so there are also some cases where this is more general than the ones that have been considered before. Okay, so here was an example, and now I come to the main result. And I think I will continue with this next week. I just want to give you a very brief overview about what it says. Okay, so recall that what is important here is that the sample size, the number of data that we have, that this is n. Okay, so that's the sample size. Now, the result comes with two assumptions on the underlying network architecture that you have to assume or to use. The first one is that you should use the depth of the network should scale like log of the sample size. And the second one is on the width of the network, and the width of the network should be larger or equal than this weight. So this is something which again depends on these parameters of the underlying function. So, but there's no upper bound on the network width. So you can take it, for instance, to be of the order n. Then you can make it you can choose it independent of all these parameters that you might not know. So it just gives you a lower bound, but it doesn't give you an upper bound. If you make it large enough, you don't have to worry about it. And there's a third thing, and that is about the network sparsity, which is essentially the crucial object in the network that really drives the regularization in this setup. So the network sparsity has to be really chosen of exactly this order, okay, up to constants, but you have really to tune it to this order. And that is what somehow in the proofs trades off the variability of the network, the stochastic variability against the approximation quantity. And if you have found a network with this property, and then for any method that returns you an estimator within this network class, you can write the prediction error. You can bound it from above and from below, up to log n factors, which are a bit nasty. But you can bound. This is not so important because it's all about these polynomial rates. So you can bound it from below and above by essentially two terms: the phi n and the delta n. So the delta n tells you essentially how good your method is, right? We haven't really said anything about the method yet. Okay, so there must be something which, if you could always return one network without, right? You get the data, you always say one network, whatever the data is, right? That would be a very bad reconstruction scheme, unless this is you made by randomness, you just guessed the right network. So there must be something in these weights that depends on the method that you're using. And the delta n here, that just measures, okay, so this is forget about this expectation, it doesn't really matter. So this is the empirical loss that all these gradient descent methods want to minimize. And so for regression, right, the cross entropy loss is just the squared L2. So you shouldn't confuse it with the way it's written for the classification. But if you do regression, this is exactly the loss that all the methods want to minimize. Okay, so typically, right, if you do gradient descent methods, you want to make that as small as possible. And this object is somehow the smallest the empirical the smallest loss that you can have over this function class of over all networks in the class. Okay, so that's the loss that corresponds to the global minimum. And all what this says essentially is that if you come close with the loss to the global minimum, maybe you get stuck in the local minimum, but if you come somehow close, then the delta n will be small. And if you're far away from the global minimum, then the delta n will be large. And because it's an upper and lower bound, it will then, if it's large, it will drive the prediction error. And if it's small, if you get the loss very small, then you make the delta n small. And then everything is driven by the phi n, and the phi n is just the statistical problem, and it's also bounded from below and above, and it's essentially it's also the optimal rate that you can achieve over this function class. So it's the best possible rate that is achievable by any method over this function class. So there's not more information in the data than to reconstruct the true function up to this error. And the deep networks, they can achieve this rate in this case. Okay, so my time is up. So there's still some slides left, and I will continue on Monday. Yeah, thank you. Mm-hmm.